Section 20 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Fred Abood. The Science, History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 14, The Moon, Part 1. That the Moon is the nearest the Earth of all the heavenly bodies is one of the most obvious facts which confront the stargazer. Its regular motion must have been early appreciated by primitive man, after he had realized that the rising and setting of the sun marks regularly recurrent intervals of time. As he was able to reflect upon his observations and properly to coordinate them, he doubtless noted the connection between the form of the Moon and its position in the sky with respect to the sun. For by keeping count with pebbles or rude notches cut in a stick, he would learn that the interval of time between recurring full moons was always the same, and that the series of changes he could observe followed in regular order. Thus, when the Moon appeared after sunset near the place where the sun had disappeared, he saw a thin crescent, the hollow side of which was turned away from the sun. A little later, the Moon set. The next night he observed the Moon, further from the sun, with a thicker crescent, and noted also that it set later, an effect that gradually increased until the semicircular disk, with the flat side turned away from the sun, was seen in rather less than a week after the first appearance of the crescent. In another week, the semicircle enlarged to a complete disk, and the Moon rose about sunset and set about sunrise, being in a direction nearly opposite to that of the sun. From this time on, the size again diminished. The semicircular form was seen once more with the flat side still turned away from the sun, and toward the west instead of the east, as the Moon approached the sun on the other side, rising before it and setting in the daytime. Again he saw the crescent, and marked that the time of rising approached that of sunrise, until the Moon became altogether invisible. 2 or 3 nights intervened, and the new Moon reappeared, whereupon the whole series of changes was repeated. In other words, this primitive man must have formulated a lunar month. All ancient records recognize this lunar month of 29.5 days, and that interval must have been adopted long before the year. By the time of Chaldean and Egyptian astronomy, however, the year was known, so that the first conception of the lunar month is lost in the mists of antiquity. The Chaldeans studied the motions of the sun and the moon. Their calendar records, which they seem to have maintained with considerable care, enabled them to discover that eclipses occurred after a period known as the Saros, consisting of 6,585 days. The nature of the Moon was, of course, to them a mystery. It was known to move around the sky. The Babylonians supposed that, having a bright and a dark side, the different phases were caused by the bright sides coming more and more into view during its movement around the sky. In the 7th century, Pythagoras taught more correctly that the Moon, like other heavenly bodies, was spherical, and that it was bright because it received the light of the sun. The phases, he rightly judged, were due to a greater or less amount of the illuminated half turned toward us, and the curve forming the boundary between the bright and dark portions of the Moon was to him conclusive evidence of a spherical shape. He was later supported in his theory by Aristotle, who made a similar clear and definite statement of the reason for the phases of the Moon. Perhaps the first systematic study of the Moon was that of Aristarchus, a famous member of the Alexandrian school, who flourished in the first half of the 3rd century and wrote a treatise on the magnitudes and distances of the Sun and Moon, which still survives. Taking the Moon when it was half full, so that a line drawn to it from the Sun made a right angle with the line from the Moon to the Earth, by measuring the angle between the Moon and the Sun, he was able to determine the ratio of the sides of this triangle and the relative distance of the Moon and the Sun from the Earth. While the method of Aristarchus was ingenious, yet the result he obtained, that the Sun was 18 to 20 times as far distant as the Moon, was sadly in error, for the actual distance is nearly 400 times. Still, the difficulties in the way of accurate observation were enormous for lack of proper instruments. Aristarchus also took advantage of the solar eclipse to ascertain the distances of these two bodies, and reasoned correctly that when the Moon sometimes rather more than hides the surface of the Sun and sometimes does not quite cover it, their diameters must vary as their real distances. He even obtained by eclipse observations a value for the diameter of the Moon in terms of that of the Earth. What would have been an excellent approximation was marred, however, by an incorrect estimate of the apparent size of the Moon, which he took as 2 degrees instead of 1/2 a degree. Nevertheless, this work was an important advance in practical astronomy. It paved the way for Hipparchus, who discussed the motions of the Moon, motions which, long before his time, were known to be irregular and much more complicated than those of the Sun. The path of the Moon is always changing, and its motions are subject to variation. Hipparchus notes that the part of the Moon's path in which the motion is most rapid is not always in the same position on the celestial sphere, but moves continuously. He was able to realize the different motions of the Moon, to distinguish the various months based upon them, and to employ the Chaldean and other early eclipse observations for determining the position of the Moon at various earlier epochs. Hipparchus really evolved a most complicated set of motions. He was aware of the shortcomings of his theory, but was unable to reconstruct it in a satisfactory manner. Following out the eclipse method of Aristarchus, Hipparchus made a determination of the relation between the distances of the Sun and Moon, measuring their angular diameters, and found that the distance of the Moon is nearly 59 times the radius of the Earth. Combining this figure for the distance of the Sun with that of Aristarchus, a value of 1,200 times the radius of the Earth was obtained, which value was employed for many centuries. Ptolemy, in the 4th book of the Almagest, discusses the length of the month with the theory of the Moon, and makes the important announcement of a further inequality in the Moon's motion, which Hipparchus had only suspected, and which was due in large part to its position with respect to the Sun. This was later termed evection, and involved a still further complication of the mathematical computations of Hipparchus, because it meant the use of an epicycle and a deferent, which was itself a moving eccentric circle, the center of which revolved around the Earth. Ptolemy's mathematics and ingenuity were able to fit his theory to observations. Although his work showed many inconsistencies which, great as he was unable to control, nevertheless it represented a notable development in astronomy. To Ptolemy, is due the parallax method for obtaining the distance of the Moon by observing its direction from 2 points on the Earth's surface, and by finding the distance between these 2 points in terms of the Earth's radius. This distance of the Moon, he estimated, was 59 times the radius of the Earth. With this value, according to the method of Hipparchus just mentioned, he computed the distance from the Earth to the Sun. He found that the distance was 1,210 times the radius of the Earth, which value was equally in error as compared with the modern figure. The actual distance is about 20 times this amount. So readily were the motions of the Moon observed, and so carefully were the records maintained, that even at an early date, much was known about its motions. These data enabled much calculation of the Moon's motion to be carried on, so that early mathematical astronomy dealt with the Moon in no small degree. Various irregularities of its motion and appearance were discussed, and practically all of the notable astronomers made some contributions to our knowledge of the satellite. Even an outline of these discussions would lead the reader far afield into the depths of mathematics, for which reason it is possible to mention only a few of the important researches and to indicate merely their general nature. The study of the Moon had a practical importance, however, as lunar positions were early used to determine longitude in navigation, and lunar tables were calculated by government and other astronomers. Nowhere was there more interest manifested in the problem of the motion of the Moon than at Greenwich Observatory, where the matter had always been a specialty of that institution. It is a curious fact, states the late Professor Newcomb in his Reminiscences of an Astronomer, that while that observatory supplied all the observations of the Moon, the investigations based upon these observations were made almost entirely by foreigners, who also constructed the tables by which the Moon's motion was mapped out in advance. The most perfect tables made were those of Hansen, the greatest master of mathematical astronomy during the middle of the century, whose tables of the Moon were published by the British government in 1857. They were based on a few of the Greenwich observations from 1750 to 1850. The period began with 1750 because that was the earliest at which observations of any exactness were made. Only a few observations were used, because Hansen, with the limited computing force at his command, only a single assistant, I believe, was not able to utilize a great number of the observations. The rapid motion of the Moon, a circuit being completed in less than a month, made numerous observations necessary, while the very large deviations in the motion produced by the attraction of the Sun made the problem of the mathematical theory of that motion the most complicated in astronomy. Thus it happened that, when I commenced work at the Naval Observatory in 1861, the question whether the Moon exactly followed the course laid out for her by Hansen's tables was becoming of great importance. For a year or two our observations showed that the Moon seemed to be falling a little behind her predicted motion. But this soon ceased, and she gradually forged ahead in a much more remarkable way. In 5 or 6 years it was evident that this was becoming permanent. She was a little farther ahead every year. What could it mean? To consider this question, I may add a word to what I have already said on the subject. In comparing the observed and predicted motion of the Moon, mathematicians and astronomers, beginning with Laplace, have been perplexed by what are called inequalities of long period. For a number of years, perhaps half a century, the Moon would seem to be running ahead, and then she would gradually relax her speed and fall behind. Laplace suggested possible causes, but could not prove them. Hansen, it was supposed, had straightened out the tangle by showing that the action of Venus produced a swinging of this sort in the Moon. For 130 years, she would be running ahead, and then for 130 years more falling back again, like a pendulum. Two motions of this sort were combined together. They were claimed to explain the whole difficulty. The Moon, having followed Hansen's theory for 100 years, would not be likely to deviate from it. Now it was deviating. What could it mean? Taking it for granted, on Hansen's authority, that his tables represented the motions of the Moon perfectly since 1750, there was no possibility of learning anything from observations before that date. As I have already said, the published observations with the usual instruments were not of that refined character which would decide a question like this. But observations of stars, which might be available, and which had been made in many instances, would have an important bearing on this work. For if an oscillation or passage of the Moon between a star and the Earth occurred, and its time registered, the path of the Moon in the heavens and the time at which it arrives at each point of the path would be determined if the time of the oscillation was known within 1 or 2 seconds. Professor Newcomb continues, "It was not until after the middle of the century, 17th, when the telescope had been made part of astronomical instruments for finding the altitude of a heavenly body, and after the pendulum clock had been invented by Huygens, that the time of an oscillation could be fixed with the required exactness. Thus it happens that from 1640 to 1670, somewhat coarse observations of the kind are available, and after the latter epoch, those made by the French astronomers became almost equal to the modern ones in precision." The question that occurred to me was, is it not possible that such observations were made by astronomers long before 1750? Searching the published memoirs of the French Academy of Sciences and the Philosophical Transactions, I found that a few such observations were actually made between 1660 and 1700. I computed and reduced a few of them, finding with surprise that Hansen's tables were evidently much in error at that time. But neither the cause, amount, or nature of the error could be well determined without more observations than these. Was it not possible that these astronomers had made more than they had published? The hope that material of this sort existed was encouraged by the discovery at the Pulkowa Observatory of an old manuscript by the French astronomer Delisle, containing some observations of this kind. I therefore planned a thorough search of the old records in Europe to see what could be learned. By good fortune, suitable observations were found at the Paris Observatory, and their relations and the method of making were studied, and everything necessary was copied. This work took some 6 weeks, but Professor Newcomb says, "The material I carried away proved the greatest find I ever made." 3 or 4 years were spent in making all the calculations I have described. Then it was found that 75 years were added, at a single step, to the period during which the history of the Moon's motion could be written. Previously, this history was supposed to commence with the observations of Bradley at Greenwich, about 1750. Now it was extended back to 1675, and with a less degree of accuracy 30 years farther still. Hansen's tables were found to deviate from the truth in 1675, and subsequent years to a surprising extent, but the cause of the deviation is not entirely unfolded, even now. One curious result of this work is that the longitude of the Moon may now be said to be known with greater accuracy through the last quarter of the 17th century than during the 90 years from 1750 to 1840. The reason is that, for this more modern period, no effective comparison has been made between observations and Hansen's tables. End of section 20.